Today we're going to start our study of nuclear physics with a brief introduction. We'll review some things that you learned in chemistry. Not that this is a repeat of chemistry. Chemistry is mainly concerned with the atoms and their interaction with each other. That interaction was strongly dictated by the arrangement of the electrons around the outside of the atoms. In this class, we're more concerned with the nucleus of the atom. Do you remember what a proton is? Define it for yourself. That's right, it's a positive charged particle found in the nucleus of the atom. We'll have notes at the end of this lecture. Do you remember what the neutron is? Define it for yourself. That's right, it's a neutrally charged particle found in the nucleus of the atom. Do you remember what the electron is? Define it for yourself. That's right, it's the negatively charged particle found in the outer regions of the atom, outside of the nucleus. What is the nucleus? It's the small, dense heart of an atom. The electron cloud, or orbitals, or shells, or energy levels are the regions outside the electron, outside the nucleus where the electron is found. This is a representation of an atom. Not very accurate, we'll soon learn, but better than most. It's certainly better than this one. If this is how you picture atoms, please stop. This is helium, or at least a representation of it, which makes up 20% of all the atoms in the universe. Hydrogen makes up 79% of the rest. Together, hydrogen and helium account for 99% of all the atoms. That doesn't leave room for much else. And atoms only make up 4.6% of all the mass of the universe. Something called dark matter accounts for 23%, and something called dark energy accounts for a whopping 72%. By the way, we have no idea what dark matter and dark energy are, so we won't be studying either of those. But what proof do we have that atoms exist, since we can't see them? One of the first proofs we have was Brownian motion. When you look at a microscope, hopefully you got to do that in biology, all the small bits, like pollen grains, are in constant vibration back and forth. Einstein proposed that these vibrations were caused because the pollen and other visible bits were small enough to be affected by the collisions with the atoms in the water they were suspended in. Based on that, another scientist actually counted the collisions and came up with an estimate of Avogadro's number. If you don't remember what Avogadro's number was from chemistry, don't worry, we won't be using it for anything. Another proof that atoms exist is that chemistry works, and chemistry is based on the existence of atoms and how they interact with each other. Here's more proof. This is a visualization produced by a computer based on data it received from a scanning tunneling microscope, or STM. This is a silicon crystal. Each of the roundish blobs is a silicon atom. Magnification here is 10 million times. An atomic force microscope, a device similar to a scanning tunneling microscope, was used to manipulate iron atoms at this company's research facility. Here's another example of atoms manipulated with an atomic force microscope. Here are silicon atoms manipulated to write the chemical symbol for silicon, capital S, lowercase I. The larger, brighter atoms are atoms of tin. Here's an organic molecule of pentacene, which has 22 carbon atoms and 14 hydrogen atoms. Hopefully you're remembering the organic molecules that the carbon atoms form rings and the hydrogen atoms hang off of those rings. Here's a model of pentacene. The atomic force microscope used to make all these illustrations has a very sharp metal tip which detects the tiny forces between the atoms. Notice the model illustrated here is scanning pentacene from the two previous illustrations. Hopefully you accept that atoms exist, but how big are they? Take the simplest atom, hydrogen, with one proton and one electron. If I could blow up the proton to the size of a tennis ball, on that same scale, where would the electron be? You want to take a guess? If that tennis ball sized proton were located at the school, the electron would be where the black circle on this map is. Is your house inside or outside that electron's orbit? Here are the sizes of the three particles. Although we have used kilograms all year, we won't be using them in this unit. Atomic mass units, symbolized by the lowercase u, is the unit used in chemistry. We will use that sometimes. But nuclear physicists prefer the unit electron volt, or in this case, megaelectron volt, and we'll even see gigaelectron volt used. And we'll be using that one sometimes. Take a moment to notice how much bigger the proton and the neutron is in this than the electron. The electron is 2,000 times smaller. It's a tiny little thing. We will learn later that the electron is a fundamental particle. The other two aren't. Another term you'll remember from chemistry, or middle school, or earlier, is element. Elements are things like hydrogen and helium, or carbon, or gold, or oxygen, or nitrogen. The atoms of each of these elements has a unique physical property and chemical properties. Things like color, or is it a metal or not a metal? Is it a gas, liquid, or solid at room temperature? What's its hardness? And so on. But what makes the elements different from each other? The number of protons that make up the atoms determine which element it is and determines its properties. In this illustration, and the ones that follow, the red circles indicate protons, the white circles indicate neutrons, and the blue circles indicate electrons. Notice that in these illustrations, the three you see here, the electrons and the neutrons are always 3. What changes is the number of protons. The first atom has 3 protons, and that makes it lithium, and makes its atomic number 3. The atomic number corresponds to the number of protons. The second atom has 4 protons, and that makes it beryllium, and its atomic number is 4. The third atom has 5 protons, and that makes it boron, and its atomic number is 5. All that changes in these 3 atoms is the number of protons, and that changes them to different elements. The atomic number always indicates the number of protons. Remember that. You probably also remember the term isotopes. Each element has a different number of isotopes. Notice that in these 3 illustrations, the protons and the electrons are always 3. What changes is the number of neutrons. In the first case, there are 3. Remember, the neutrons are in white, the red are protons. In the second case, there are 2, and in the third case, there's 1. Varying the number of neutrons produces different isotopes of an element. The symbology at the bottom is called isotope notation. The letter are the single letter or double letter abbreviation for the element. In all these cases, Li for lithium. The lower number is the atomic number or number of protons. In all these cases, it's 3 for lithium. The upper number is the count of protons and neutrons. So if we vary the number of protons, we get different elements. If we vary the number of neutrons, we get different isotopes. What happens if we vary the number of electrons? We get different ions. Notice that in these 3 illustrations, the protons and the neutrons are always 3. What changes is the number of electrons. These are 3 different ions of the element lithium. The numbers at the bottom are the charges on the atom. The negative charge of the electrons are canceled by the positive charge of the proton. So, as in the first case, where the atom has 3 protons and 3 electrons, the atom has no charge. In the second case, there is 1 extra electron, so the atom has a charge of -1. And in the third case, there is only 2 electrons, so the atom has a charge of +1. So for your notes, we have a few coming. So pause if you need to. The proton, the positively charged atomic particle, which is located in the center of the nucleus of the atom. And the number of protons designates the atomic number, which determines the unique nature of the atom. Jot down somewhere, number of protons equals atomic number. You'll need that for your assignment. Neutron, the atomic particle of no charge, which is located at the center of the atom. Neutrons are believed to serve a function of holding the nucleus together. The electron, the negatively charged particle that can be found in the region of high probability outside the nucleus. An element, the substance composed of atoms having an identical number of protons in each nucleus. There are 92 naturally occurring elements and 26 artificially created or lab-created elements. And remember, for your assignment, the number of protons equals the atomic number. The mass number, the number of protons and neutrons in an atom, jot down mass number equals protons plus neutrons. You'll need that for your assignment. Isotope, atoms of the same atomic number or element, but different number of neutrons. Some isotopes are stable and last indefinitely. Some are unstable and decay. More on this on another day. Weighed averages of the isotopes of an element is equal to the atomic mass. Don't confuse atomic mass with atomic mass number. They are different. Atomic mass is the real number that you usually see on a periodic chart for each of the elements, as in this case with carbon, the 12.011. They are averages, so they come out as real numbers. Again, they're not the same as mass numbers, which are the count of the protons and neutrons, and so must be whole numbers. So, what are these averages called atomic mass average? What are they averages of? Here's a list of the known isotopes of carbon. There's quite a few of them. Notice that only two are stable, carbon-12 and carbon-13. The rest are unstable and will change to something else. Again, we'll learn about that on another day. If I have a sample of carbon, it will be made up of all of these. To find out its mass, I would need an average of all of these. But since most of the sample will be carbon-12, notice that it's 98.9% of the sample, I must give more weight to this carbon-12 when I'm calculating my average. In other words, I have to calculate a weighted average. Here's how you would calculate the average atomic mass for carbon. The units here are in atomic mass units. We only use the two stable isotopes to do the calculation, carbon-12 with an abundance of 98.9%, and carbon-13 with an abundance of 1.1%. So notice we take those percentages, 0.989, times 12, because that would be the mass of carbon-12, and 0.011 times 13, which would be the mass of carbon-13. We add those numbers together, and that calculation will get us to 12.011, and those are atomic mass units. Okay, so you don't really have to do this calculation, since this number is always found on most periodic charts. Just so you know how it's different and that it's not the same as the mass number. One thing you'll need to do for your assignment is write isotope notation. So jot down this diagram. The capital X is the chemical symbol for the element. The lower number you'll find, which is represented by Z here, is the atomic number, or the number of protons. And the upper number is the mass number, or number of protons plus number of neutrons. Here's an example of isotope notation for the three isotopes of hydrogen. Notice H, capital H is the symbol for hydrogen. The 1 is the atomic number or number of protons. And then in the first one, the upper one is the number of protons and neutrons, which means it doesn't have any neutrons. The second one has 1 proton, 1 neutron. And the third one down, the tritium, has 2 neutrons and 1 proton.